Next slide. In this slide and the previous slide, we get into just the basics of weather with just a brief introduction to some of the key ideas. At Bakersfield College, we have an entire semester course devoted to the study of weather and climate called meteorology that I encourage you to check out for a more in-depth treatment, but still at the first year college science level. This slide talks about the difference between weather and climate. Weather is the ever-changing combination of winds, clouds, temperature, and pressure at a particular location and time. Climate is the long-term average of weather, usually 30 years or longer for Earth climate, which means it can change only on much longer timescales. The long-term averaging removes the chaotic wiggles, making it possible to make long-term predictions of future climate. If you've ever heard someone say something like, "How can we expect to forecast the weather in 100 years, let alone 100 millennia, if we can't do it for 10 days?" Then you've heard climate being confused with weather. The answer is that no one is attempting to forecast the particular weather to expect on a particular day a century from now. Individual weather fluctuations are chaotic in the physics sense of the word chaos. Look up the butterfly effect for more about that. The time-averaged weather, climate, is not chaotic. Weather predictions versus climate predictions is analogous to not being able to predict if a particular coin toss will be heads or if it will be tails, but you can easily predict the statistical results of a large number of coin tosses. Another analogy David Archer uses in his book, The Long Thaw, involves water in a sink with water flowing into it via a faucet and water flowing out via a drain. Weather is like the ripples on the surface of the water, while the average water level in the sink would be climate. Predicting the average water level in the sink is much easier than predicting all the features of the individual ripples on the surface. Climate is constrained by the simple system-wide energy budget of energy input and energy output, just as the water level in the sink is constrained by the water flowing in from the faucet and the water flowing out through the drain. The major things that affect a region's climate are illustrated here: global rainfall, mountain ranges, and the rain shadow effect, and ocean currents. Note that all parts are connected to each other, so a change in one part of the globe will cause changes in other parts of the globe. Climate models have to take all this into account, not to mention all the feedback loops that can amplify or dampen, reduce an effect. The rainbow-colored world map describes how the ocean can transport energy. The colors correspond to temperature of the water, where red is very warm and dark blue is very cold. If you select the picture, it enlarges it so it's easier to read the labels. The California Current is a current in the Pacific Ocean that moves southward along the western coast of North America, from British Columbia to southern Baja California. The movement of the cooler northern waters southward makes the coastal waters cooler than the coastal areas of the eastern United States at the same latitudes. The Gulf Stream is a warm surface ocean current born in the Gulf of Mexico that flows up the eastern United States seaboard and then veers northward toward Europe at about 6 kilometers per hour, 4 miles per hour. The North Atlantic Drift, aka North Atlantic Current, continues carrying the warm water north of the British Isles to Scandinavia. This warm water makes Western Europe have climate more like the United States instead of Canada, of which it shares the same latitude range. Northern Norway is near the Arctic Circle, but most of its coast remains snow and ice-free, even during the winter. I have a link to a really nice NASA video about ocean currents and salinity, or the concentration of salts in the water. Here again is the picture I showed in the previous lecture of the hydrological cycle or water cycle on Earth. The cycling of water from liquid in the oceans to gas in the atmosphere to condensation in clouds to precipitation and runoff as streams and rivers back to the ocean. Recall the important role of clouds in transporting energy. 1, they block energy from the sun, a cooling effect, and 2, they trap energy from the surface, a heating effect. It is difficult to figure out which effect has greater long-term significance and how the temperature will change over time periods of years. Clouds are also extremely hard to model because they're so variable and changeable. The formation of clouds is also part of an energy transfer process because the evaporation process absorbs heat, while the condensation process releases heat. Also, remember the effect of mountains on the amount of precipitation a region can experience due to the rain shadow effect. Geological records show that climates can change, but most of the time the changes occur gradually over decades, centuries, or millennia. Careful study of the polar ice caps on Mars and other surface features show that Mars has also undergone climate changes, some drastic. Venus was once a more comfortable place, but it underwent a drastic global climate change as well to become a hellishly hot and very dry place. There are 4 ways that climate can change: solar brightening, changes in the orbit and axis tilt, changes in reflectivity, and changes in greenhouse gas abundance. And the timescales for each are different. The sun's brightness has increased by about 30% since it formed 4.6 billion years ago. It takes many tens of millions of years for the change to be noticeable, but this gradual brightening is what will make complex multicellular life impossible on the Earth in about 1 billion years from now. The other ways climate can change occur over much shorter timescales. And in the case of Earth and Mars, they have made them cooler now than they were in the past, instead of hotter. Gravitational interactions of the planet, its moons, and the other planets of the solar system can cause the tilt of the planet's rotation axis to change, and the planet's orbit to change shape and orientation in a periodic way. In addition, the rotation axis precesses. Put all these agents together, all with different periods, and they can create dramatic changes in a planet's climate by changing the insolation, the angle of sunlight hitting a given point on the planet's surface, and the amount of solar radiation reaching the planet's surface. These take place over tens of thousands to hundreds of thousands of years. For Earth, its axis tilts between 22 and 25 degrees over a period of about 41,000 years. Larger tilt creates more extreme seasons, warmer summers and colder winters. A smaller tilt is thought to bring about ice ages because the milder summers allow ice and snow to last throughout the year in the higher latitudes, closer to the poles. Mars's axis tilt changes over a much larger range of 13 to 40 degrees over about 100,000 years because it has no large moon to stabilize it like Earth has. Mars also feels the gravitational influence of Jupiter more than does Earth. Earth's orbit shape, its eccentricity, fluctuates over cycles of 100,000 and 400,000 years. Mars's orbit undergoes larger fluctuations of eccentricity. Finally, the direction of the rotation axis and the orbit plane also wobble or precess. This is why our North Star changes over the millennia. Earth's rotation axis precesses with a period of 26,000 years, and its orbit perihelion point shifts with a period of 21,600 years. Milankovitch was the first one to calculate the complex combination of these various periodic effects, and now we know that the 100,000-year cycle is the more powerful one that explains the 100,000-year cycle of ice ages we've experienced over the past at least 2 million years. These effects are called Milankovitch cycles in his honor. The amount of ice on the surface and clouds and aerosols in the atmosphere from volcanic eruptions and forest fires affect how much sunlight gets absorbed by the planet. More reflectivity means a cooler planet. Water ice reflects about 95% of the sunlight that hits it, while liquid water absorbs about 95% of the sunlight that hits it. That's why we expect the rate of change in our global temperature to increase as more of the polar ice caps melts. The polar ice caps have played a major role in keeping Earth comfortable for us. The time period for reflectivity changes is measured in decades and centuries. Here's just a quick reminder of what is the greenhouse effect. Visible sunlight reaches the surface and heats up the surface. The surface glows in the infrared. Certain gases like carbon dioxide or water vapor in the atmosphere prevent this infrared energy from leaking out to space. This heats up the surface even more until a balance is reached where the amount of solar energy flowing inward to the planet equals the amount of infrared energy flowing outward from the planet. The greenhouse effect is what made Venus become so hellishly hot. Changes in the amount of greenhouse gases can change the heat trapping effect. More greenhouse gases warms a planet, and less greenhouse gases cools a planet. On Earth, water vapor accounts for more of the greenhouse effect than carbon dioxide because of the large amount of water vapor in the air. But per molecule, carbon dioxide is a much more powerful greenhouse gas. The amount of water vapor is also more sensitive to the temperature, changing within a few days. When the temperature drops, water vapor condenses and precipitates out, reducing the greenhouse effect. When the temperature rises, liquid water evaporates to make more water vapor, increasing the greenhouse effect. In this way, water vapor is an enhancer of climate change instead of an agent of change. Water vapor creates a positive feedback. A positive feedback enhances whatever initial change is made in the system. Carbon dioxide, on the other hand, stays in the atmosphere for decades to centuries, so it can be an agent of change on a planet. Similarly, methane, which per molecule is an even more powerful greenhouse gas than carbon dioxide, can be an agent of climate change on a planet. The time period for greenhouse effect changes is measured in decades and centuries. For both Mars and Earth, the Milankovitch cycle effects are the main triggers for going into ice ages and coming out of them, while the resulting changes in reflectivity, ice coverage, and greenhouse gas abundance changes have made the temperature swings, cold to hot and back to cold, be much greater and faster than they'd otherwise be. For Earth, they've enhanced the temperature swings by about a factor of 2 times. All 4 of these processes occur for any planet anywhere in the galaxy.